Chapter 6, Chemical Equilibrium, Section 6.1, Gibbs energy of reaction and reaction quotient. For reactions that involve only ideal gases, the Gibbs energy of reaction depends on the partial pressures of these gases. Here's the example. We have reactants A and B, products X and Y. Nu sub A, nu sub B are the coefficients for the reactants. Nu sub X and nu sub Y are the coefficients of the products. Now the Gibbs energy of reaction is the Gibbs energy of the products minus the Gibbs energy of the reactants. Therefore, we can write out this equation. On the left hand side, we have Gibbs energy of the reaction. And on the right hand side, we have all products minus all reactants. We need to take care of the coefficient here. And this is simply the Gibbs energy of formation of species I. And I is one of the products. Over here, we use the same notation for the index I. However, this I has to be one of the reactants. Again, it's products minus the reactants, because the final state is the products. The initial state of the system is the reactants. Now we have this equation. So for species I, the Gibbs energy of formation is equal to the standard Gibbs energy of formation plus a correction term. Over here, we take the actual pressure of species I into account. So over here, we can see this is just the general Gibbs energy of formation. This is the Gibbs energy of formation when the partial pressure of species I is exactly 1 bar. So there's a difference, and this RT times the natural logarithm of Pi over P naught takes the difference into account. Again, I is a simple dummy index for all reactant species here, and I is the dummy index for all products here. Now let's rewrite this equation. This time the Gibbs energy of reaction is equal to, again, we have 2 products and then we have 2 reactants. We take the difference, and over here, if you look at this species X, the Gibbs energy of formation of X is the standard Gibbs energy of formation of X plus this correction, RT times the natural logarithm of the partial pressure of X over P naught. So this term is equal to this term plus this term. And same for Y, same for A, same for B. So now from 1, 2, 3, 4 terms, we have a total of 8 terms. The first 4 terms together is going to be the standard Gibbs energy of reaction, in which every single species is in a standard state. For an ideal gas, it simply means its partial pressure is 1 bar. And now we have 4 terms over here. They take the pressure difference into account. P naught is the standard state, but X does not have to have 1 bar pressure. It can be any pressure denoted by P sub X. And this is partial pressure of Y, partial pressure of A, and partial pressure of B. So that's why we have these 4 terms that take the pressure difference into account. We can even combine these 4 terms to get this. It's going to be RT times the natural logarithm of Px over P naught to the power of nu x, Py over P naught to the power of nu y, Pa over P naught to the power of nu a, Pb over P naught to the power of nu b. So you can see we have X and Y on top, A and B on the bottom. Products on top, reactants on the bottom. So really, the Gibbs energy of reaction is equal to the standard Gibbs energy of reaction plus some correction based on the partial pressures of X, Y, and A and B. Now introduce a concept, reaction quotient of pressures in this section. Q sub P is the reaction quotient of pressures. This is the expression of Q sub P, products on top, reactants on the bottom. And we have Px over P naught to the power of nu x, Py over P naught to the power of nu y. These two are the products. And similarly, we have reactants on the bottom. Q sub P is unitless because Px over P naught is unitless. Same for this, this, and this. They're all unitless. And now we have a simpler expression. The Gibbs energy of reaction is equal to the standard Gibbs energy of reaction plus RT times the natural logarithm of the reaction quotient of pressures. When the reaction reaches equilibrium at constant temperature and pressure, the Gibbs energy of the reactant is equal to the Gibbs energy of the products. Now we have delta G of R equals 0. The Gibbs energy of reaction is just 0, and therefore we can set this whole thing to be 0. The standard Gibbs energy of reaction plus RT times the natural logarithm of K sub P is equal to 0 at equilibrium, and then we have the standard Gibbs energy of reaction equals negative RT times the natural logarithm of K sub P. What is K sub P? K sub P is simply this, Q sub P at equilibrium. So K sub P has a name. It's called the equilibrium constant of pressures. This P stands for pressures, and K sub P is the equilibrium constant of pressures. Again, K sub P is simply Q sub P at equilibrium. And then after we write this Q sub P, so this is Q sub P, we need to add EQ in the subscript. And we can compute K sub P given the standard Gibbs energy of reaction. So K sub P is equal to e to the power of negative standard Gibbs energy of reaction over RT. Now how do we get this? This delta G of R in the standard state is simply the Gibbs energy of formation of all products minus the standard Gibbs energy of formation of all reactants. This is just the difference between the reactants and the products. In the previous chapter, we have learned that the criterion for spontaneity in a closed system with no non-expansion work is unified to this. The sum of mu I dn I is less than 0. At equilibrium, neither direction of the chemical reaction is spontaneous, and therefore the sum of mu I dn I should be equal to 0 at this chemical equilibrium. Now we have this equation, and we also have dg is equal to negative s dt plus vdp plus the sum of mu I dn I. Over here, this equation holds for any closed system, even if there is chemical reaction taking place in the system. Now if this is 0, if the sum of mu I dn I is 0, then we have dg is equal to negative s dt plus vdp at equilibrium. Now if temperature and pressure are constant, we can say dt is 0, dp is 0, therefore dg becomes 0. So the total Gibbs energy of all substances remains constant at this equilibrium under the constant TP condition. So when do we know the chemical equilibrium has been reached? Well, if it's constant temperature and constant pressure, we know this chemical reaction reaches the equilibrium when dg is 0. More specifically, G has been minimized when temperature and pressure are held constant in a closed system with no non-expansion work when this chemical reaction reaches equilibrium. So again, at equilibrium, G is minimized. Since it's minimized already, dg is 0. Now given this equation from the previous chapter, dA is negative s dt minus pdv plus the sum of mu I dn I. We know at equilibrium the sum of mu I dn I is 0, and therefore dA is equal to negative s dt minus pdv over here when the chemical reaction reaches its equilibrium. The total Helmholtz energy of all substances in the system should remain constant at equilibrium under the constant temperature and volume condition. We can just look at this equation. When temperature and volume are constant, dt is 0, dV is 0, therefore dA is 0. More specifically, A is minimized at equilibrium when temperature and volume are held constant in a closed system with no non-expansion work. Now, what if there is some non-expansion work, like electric work? When there is electric work, then dA is less than or equal to dW of this electric work under the constant TV condition. And in this case, if there is electric work, then dG is less than or equal to dW electric.